Hi again. Welcome to the next video, which introduces the basic concept of one aspect of the topic of calculus. That is the concept and technique of differentiation. Here we develop a method to determine the gradient of a curve at any given point on that curve. In the next videos in this calculus series, we refine the techniques developed here to enable us to differentiate more quickly and in more complex situations. The topic leads us to being able to analyse the main aspects of a curve, which in turn enables us to analyse very complex situations modelled by equations. Differentiation is a major and very important topic in mathematics. To begin our approach, draw two coordinate axes, we'll label them, and then let's draw some random curve which we indicate here in blue. We will refer to the equation for this curve as y equals fx, that is, it represents some function of x. Now draw a tangent to this curve. Our problem is now revealed. Gradient is generally defined as being rise over run between 2 points. But if we look at the point where the curve and the tangent meet, there is only one point, so no rise, no run. We therefore have to construct a situation to enable us to find a rise and a run. To do this, draw a secant to the curve. A secant, of course, is a chord that just keeps on going in both directions. Let the secant join the first point of contact between the tangent and the curve to some other random point further along the curve. Label the x-axis under the first point of contact as x. Let the distance along the x-axis to the second point of contact be h. Therefore, the second point of contact has the x value of x plus h. Label the first point of contact, that is, the one between the curve and the tangent, with the coordinates x and fx. Then label the second point of contact between the curve and the secant with the coordinates x plus h and fx plus h. It is now possible to define a gradient for the secant drawn between the 2 points as being the difference between the y values, fx plus h minus fx, divided by the difference between the x values, x plus h minus x. Our approach is now to move the second point of contact between the curve and the secant down the curve so that it becomes closer to the point of intersection with the tangent. As this process of moving continues, the gradient of the secant decreases until, in the limiting case, the secant will touch the curve at only one point, at which time it will be in effect the tangent. So the gradient of the tangent is the limiting value of the gradient of the secant. We will now apply these ideas to a real example with the aim of obtaining a function from which we can calculate the gradient at any point. Take the parabola fx equals x squared minus 2x plus 4. Step 1 is to write down our approach to calculating the gradient, which we just wrote out before. The letter m stands for gradient, and I have used the Greek letters delta to represent the large or finite differences between the y values and between the x values as the secant moves. Using standard function notation, substitute for fx plus h and for fx, then expand the brackets, simplify, and then factor out the common factor of h. Cancel to obtain a simplified function for the gradient, but one still involving the difference between the two x values at any given point in time, that is, at any value for h. The diagram shows that as the secant moves down the curve, h becomes smaller. Finally, the value of h is approximately 0. We are therefore now able to define our gradient function from our original function fx as being the limit reached when the infinitesimal changes in h become 0. A gradient function is indicated by writing it as dy dx with normal d's, showing that the limiting position as h approaches 0. So we're going to use dy dx quite a number of times. So dy dx is equal to 2x minus 2. The equation can now be used just like a formula to calculate the gradient of the original function represented by the blue curve given any value of x. So for example, if x is equal to 1, dy dx is equal to 2 times 1 minus 2, which is 0. When x equals minus 2, dy dx equals 2 times minus 2 is equal to minus 6. So in the second example, the curve has a negative gradient, so it's sloping downwards, and it's reasonably steep. In summary of our discussion, the technique of differentiation seeks to determine and use the concept of gradient or slope. So you will always keep in the front of your mind that differentiation emphasises gradient or slope. The technique of first principles, which we've described here, uses the basic concept of gradient to develop a function or an equation with which to calculate a gradient at any point on a given curve. So these are the steps you will follow each time you need to differentiate by first principles. Follow them exactly. Go and do some exercises in Test Yourself 1 on my website, drjsmaths.com, by hitting the back button. Refer to the solution so that you can ensure your setting out is exact. There's not too much room for changing things here. Hope I have helped you develop your approach to differentiating the long way. In the next video, we will examine ways to shortcut this long approach. Hit the like button and subscribe if you haven't already to keep up to date with new videos as they are released. Add a comment or send me an email if you've got any questions. Good luck with differentiation, so important. See you on the flip side.